Thus far in this class, we've looked at tests designed to assess the statistical significance of a difference between means. For example, the one-sample t-test compares the mean from a sample with the mean from a population. The independent sample t-test looks at the difference between two independent samples. The analysis of variance that we studied is for differences between three or more means. In each case, however, we were only focused on a single variable. Often it was IQ score, could have been something else. We're now going to move into talking about relationships between variables and whether or not they are significant. Suppose we have a study looking at the effect of gender on attitudes towards something like capital punishment. If I know your gender, does that give me the ability, or does that improve my ability to predict your attitude towards capital punishment? For example, maybe men are more likely to favor capital punishment than women. That's the kind of relationship we're interested in these tests that we'll be looking at. We can perform these calculations and analyses on multiple variables all at once, but we're going to focus on two variable problems just because the math is a lot simpler and there are much better tests for assessing multivariate relationships. The place to start with all this is in looking at a contingency table or a crosstab table, because that's how we're going to display our data, and that's what we need to do to get started with these kinds of techniques. Let's take a look at a contingency or crosstab table. Okay, so this table shows the relationship between a survey respondent's race and his or her political party. By convention, we set tables up so that the independent variable is in the column position and the dependent is in the row position. Each of the cells shows the number of respondents in both categories. So there are 96 white respondents who identified as Democrats. There were 54 African American respondents who identified as Democrats, etc. These values shown here in green are called the cell counts or observed values. If we read across the table, we can see that 150 Democrats, 150 Republicans, and 100 independents responded to the survey. Reading down the columns, we can see there were a total of 300 whites and 100 African Americans. The row and column totals are called, respectively, the row marginals and the column marginals. A total of 400 people completed the survey. So let's return to the question we started with. Does knowing a person's race help predict their political party affiliation? Well, as the table shows, there are more whites who are Democrats than there are African Americans, 96 as compared to 54. But of course, there are more white respondents overall. There are 300 compared to only 100 African American respondents. So clearly, looking at these counts doesn't make much sense. We need to look at percentages. In this table, we computed the percentage of whites and African Americans in each political group. This is important. Notice that we computed these percentages for each level of the independent variable. In order to see whether changes in an independent variable affect a dependent variable, we have to compute these percentages this way. The easiest way to remember to do this is to place the independent variable in the column position and then to percentage down the columns. In this table, we've percentaged across the rows. There really isn't that much of interest we'd be able to say with a table like this. So what, in other words, if 64% of the Democrats in our sample were white? All we're really doing here is making a statement that describes some characteristic of the population. Since there are more whites in the United States than African Americans, you'd expect that there would be more whites in each political party. So this really is not very interesting. We could also have percentaged the table this way. All this tells us is that 24% of the people in our sample are white and Democratic, 14% are African American and Democratic, etc. There's nothing interesting here because we're not saying anything about any of the relationships between the variables. For that, let's go back to our original table where we percentaged down the columns. All right, so again, you can see that knowing your race helps me predict your political party affiliation. If I know that you're African American, for example, I know there's a much better chance you'll be a Democrat. Why? Because 54% of African Americans are Democrats. Similarly, if I know that you're white, you're nearly twice as likely to be a Republican. Again, why? Because 41% of all whites are Republican, a larger percentage than for any other political party. Now the question becomes, are these predictions based on differences which are statistically significant? All right. So how do we determine statistical significance with these kinds of data? Well, the answer is to compare the observed cell counts with the cell counts we would expect if there was no statistically significant relationship. In order to do that, we need to compute the expected cell counts. So here again are our observed cell counts. The first thing you might notice is that 3/4 of our respondents are white and 1/4 are African American. Here's the thing. If 3/4 of all our respondents are white, then we would expect, if there was no relationship between race and political party affiliation, we'd expect that 3/4 of our Democrats would be white, that 3/4 of our Republicans would be white, and that 3/4 of our independents would be white, plus or minus, of course, some random variation. To calculate the expected counts in each cell, we simply multiply the total number of Democrats, in this case there are 150 Democrats, by 3/4. This gives us an expected cell count of 112.5. 1/4 of the total sample is African American, so by the same logic, we'd expect that 1/4 of the Democrats would be African American if there was no relationship between race and political party affiliation. So again, if there are 150 Democrats, we'd expect that 37.5% of our respondents would be African American and Democrats. To figure the expected values for each cell, you multiply the row marginal for that cell by the column value for that cell and divide by the total n in the sample. This table shows the results for all 6 cells. You'll note that in this case, because there are 150 Democrats and 150 Republicans, the expected cell values are the same for whites and the same for African Americans. That's just purely a coincidence. The statistics we use to determine whether a relationship is significant is called chi-square. Chi-square is equal to the sum of each observed value minus its corresponding expected value, squared, divided by that expected value. Why? Well, the numerator of this formula is similar to the general formula for tests of statistical significance that we've been using throughout the course. It's an observed difference minus an expected difference. Unlike the other tests we've looked at, the denominator is not a standard error, but simply the expected value. A standard error just doesn't really make much sense when you have a categorical variable. But the ratio functions the same way. If the observed value is very different than the expected value, likely in a statistically significant relationship, the numerator goes up and the value of the fraction goes up at the same time. As usual, the higher the value of the test statistic, the more likely it is that we reject the null hypothesis. So as we've done in the past, the easiest way to solve a problem like this that involves summation is to set up a summation table. Here's the calculation table for this problem. To compute chi-square, we simply sum the values in the rightmost column of the table. In this case, the value of chi-square turns out to be 15.52. Just like z and t and f, chi-square has a probability distribution, and we therefore need to look up a critical value for that distribution in a table. To do that, we first need to calculate the degrees of freedom we're working with. For chi-square, the degrees of freedom is given by the number of rows in the table minus 1 times the number of columns in the table, also minus 1. In this case, there are 3 rows and 2 columns, so we have 3 minus 1 times 2 minus 1, which equals 2. With that value computed, the values of chi-square, I should say the critical value of chi-square is something we can look up. Here is a sample chi-square table, and you can see if we read the degrees of freedom down the rows and the alpha level across the columns, in this problem with 2 degrees of freedom, you can see that we have a critical value of chi-square for 5.9915. Based on our expected values, we calculated a value of chi-square of 15.52, so we can reject the null hypothesis and conclude that there is a statistically significant relationship between race and political party affiliation. That's pretty much it. Conceptually, chi-square operates in a way similar to the other tests of significance that we've been working with. It answers the question, are the observed differences between the cell counts different from what we would expect to see if there was no relationship between the variables? It's worth pointing out that we can use chi-square for any number of columns and rows, though interpreting the results for a contingency table with many rows and/or many columns becomes impractical, and there are better techniques to use in those circumstances. Before we finish up, let's just note that in order to use chi-square, we need to be sure that the expected count in each cell is at least 5 cases. For tables with only 2 or 3 levels for each variable, this is usually not a problem. But if you start getting into tables with more than 2 variables or multiple levels for each variable, things can start to get tricky. For these kinds of problems, there are better techniques to use, but they're a bit beyond the scope of this course. Okay then.